All right, let's dive into a classic, super powerful, and let's be honest, sometimes confusing tool from the programming world, System V Semaphores. If you've ever looked at them and thought, what is going on here, you are definitely in the right place. So picture this. It's one of the biggest headaches in concurrent programming. You've got 2, 3, maybe a dozen different programs all trying to write to the same file at the exact same moment. What do you get? You get chaos. You get corrupted data. You get a really, really bad day. So how do we actually manage this and bring some order to the madness? Well, one of the original, tried and true answers to this problem is the semaphore. The best way to think of them is like traffic cops for your code. They stand at the intersection of your shared resources and tell processes when to stop, when to wait, and when it's safe to go. So what's the big deal with System V Semaphores? Unlike some of the simpler locks you might have run into, their real magic isn't in just one thing, but in the fact that they operate as this powerful collection. This slide really puts it into perspective. A basic binary semaphore is like a light switch. It's either on or off, available or not. Simple. But a System V Semaphore set, whoa, that's a whole different animal. It's an entire array of counters. This means you can manage a whole pool of resources, say 5 available database connections, and you can perform these really complex operations on the whole group all at once, atomically. To really make this click, let's use an analogy that we're going to keep coming back to. I want you to think of the semaphore set as a key cabinet, and each individual semaphore inside that cabinet, that's a hook. And on that hook, you can hang one or more identical keys for one of your resources. Okay, so we've got our key cabinet analogy. How do we actually build one? I mean, before any process can go and grab a key, the cabinet has to exist. In the world of System V, making that happen is the job of one specific system call, semget. Its purpose is beautifully simple. You give it a name, and it either creates a brand new semaphore set for you, or it finds an existing one and gives you the handle to it. That's it. Let's break this down with our analogy. That first parameter, key, that's the unique label you stick on the front of the cabinet so any process on the whole system can find it. And sems, that's you deciding how many key hooks you want inside. And semflag has all the instructions like IPC_create, which is you telling the system, hey, if this cabinet doesn't exist, build it for me. And right here, we hit our first major gotcha. This is a classic trap that gets everyone. Just because you've built the cabinet with semget, that does not mean there are any keys on the hooks. The initial values are, well, they're garbage, random junk. You absolutely must initialize them yourself before anyone tries to use them. So our cabinet is built, but we still need to actually put the keys on the hooks. Now, we'll get to initialization in just a moment, but first, let's jump to the main event. How do we actually use the keys? This is all handled by the semop function. Semop is pretty cool. It works by taking this little blueprint of what you want to do. You tell it which hook to go to, sumnum, what action to take, like take a key, return a key, or just wait till the hook is empty, semop, and then any special flags. And let me tell you, that semundo flag is an absolute lifesaver. It basically tells the operating system, look, if my process crashes while it's holding a key, please put it back on the hook for me. This is huge for preventing deadlocks. Okay, let's walk through this. Imagine we've properly initialized our first hook, semaphore number 0, to a value of 3. What does this mean? It means there are 3 keys hanging there, ready to be used. 3 resource slots are available. Now along comes a process, and it needs one of those resources. It performs what's traditionally called a P operation. All that is a fancy term for decrementing the counter. It calls semop and tells it to perform an operation of -1. So here's what happens all in one atomic step. The system checks, is the value greater than 0? Yes, it's 3. So it subtracts 1. The count becomes 2, and the process gets the green light to proceed. 1 key has been taken. Now, if the value had already been 0, that process would have been put to sleep, forced to wait right there until a key was returned. All right, later on, the process finishes its work. It's a good citizen, so it has to return the key. It does this by performing a V operation, which, you guessed it, just means incrementing the counter. It calls semop with an operation of +1. And just like that, the count goes back up to 3. Now, here's the cool part. If another process had been blocked, waiting for that key, this V operation would instantly wake it up, allowing it to grab the key and get back to work. It's a really elegant system when you see it in action.
So we've seen semget to build the cabinet and semop to use the keys. But what about managing the whole thing? Putting the keys on the hooks in the first place or tearing down the cabinet when we're all done? For that, we need semkudel, the Swiss Army knife of semaphores.
Seriously, SemControl does everything else. Most importantly, it's how we solve that initialization problem we talked about. Right after you create a set with semget, you use SemControl with setval to put the right number of keys on each hook. And then, when your entire application is shutting down, it is absolutely critical that you use IPC RMID to tell the system we're done here. You can destroy this set now.
And speaking of SemControl, here's our second big gotcha, and this one is famous. To pass some of the arguments that SemControl needs, you have to use this special data structure called union semunion. Now, for some wild historical reasons, this union is often just missing from the standard system header files. Yeah, you heard that right. It means you, the programmer, have to literally copy and paste its definition into your own code. It's like a weird rite of passage for anyone learning System V.
Okay, we've looked at all the different pieces of the puzzle. Semget for creation, semop for operation, and SemControl for control. Now let's put it all together and walk through the complete journey of a semaphore set, from birth all the way to death.
This right here, this is the whole playbook. If you remember anything, remember these 4 steps in this exact order. First, one process has to be the one to create the set. Then that same process must initialize the values. After that, any number of processes can use it, taking and returning keys. And finally, and this is so important, when everything is done, one process has to take responsibility for destroying the set. If you skip initialization or you forget to destroy it, you are signing up for a world of pain and bugs.
So there you have it, System V Semaphores. They are an incredibly flexible and powerful tool. They let you manage entire pools of resources and do complex atomic operations that are really hard to do with simpler locks. But all that power comes with complexity. You've got the manual initialization, the mandatory cleanup, that quirky semun union you have to define yourself. Today, we have more modern tools like mutexes and condition variables. So the question I'll leave you with is, knowing what you know now, when would you reach for this powerful, classic, but complex tool?